This is the Building Automation Monthly Podcast with Phil Zito, episode 157. Hey folks, Phil Zito here, and welcome to episode 157 of the Building Automation Monthly Podcast. In this episode, we will be continuing our four-part series on the 4 tiers of a building automation system. So here's kind of a quick recap. The average BAS consists of 4 tiers. Those are servers, supervisory devices, field controllers and trunks, and inputs and outputs. So in last week's episode, we went really deep into inputs and outputs. We talked about logical points, physical points, input types, output types, and just how all of that works together. So this week, we're going to be diving deep into controllers and trunks. We're going to talk about how controllers came about, how trunks came about, what you need to know, the insides and outsides of controllers, how they work, how trunks work, what signaling is, all sorts of fun stuff. You're going to get really deep into these different topics. Now, before we do that, I do want to remind you that this episode is sponsored by our course, Building Automation Systems Fundamentals. This course is the perfect introduction to building automation systems. Before you ever go to a manufacturer training course, before you ever go and actually take tools out in the field, you should definitely go through this course. It will ground you in everything you need to know so that you can really succeed in your career. And some of our students have wonderful things to say about the course. Here's just a couple of them. So Gary from a major BAS manufacturer says, I feel that anyone working in the controls field should learn this material. It's definitely very informative and can propel the average HVAC guy further in his career. Jason from a major BAS manufacturer says, Phil is a great teacher with a great personality and attitude. He is able to explain the subject matter very clearly and keep it interesting. So if you want to go and take your career to the next level, the BAS Fundamentals course is the first step. And I encourage you to go to buildingautomationmonthly.com/157, scroll down to the BAS Fundamentals logo, click on that logo, and enroll in the course. All right, so controls. That's the word we use to define our trade, yet so often we can't really describe what a controller is. I mean, surely we can describe, hey, the controller is the device that we put on a piece of equipment or in a panel. It takes the inputs, using some sort of logic, it processes those inputs and drives outputs. But really, I mean, what is making that happen? What do we need to know about controllers that we don't know? Now, I found that in order to truly appreciate the reason why controllers function the way they do, we need to go back to a much simpler time, a time when most of controls were still pneumatic. Now, contrary to popular belief, pneumatic controls actually could communicate with one another via pressure signals. I know that's kind of weird, but they actually could. Now, the deal is that while they could communicate, they were severely limited. I mean, you literally could only process the pressure signal and make one of 2 choices. You could either have a Boolean response through a solenoid, or you could go and drive a valve or drive an inlet vane through some form of analog response. I mean, that was all you could do. Yeah, sure, there were accumulators and things like that, but the issues that existed with pneumatics, I'm not going to get into a pneumatics versus DDC debate. The reality is pneumatics are old technology and controls are new technology. And yes, properly maintained pneumatics can be very accurate. The key word being properly maintained. Just the amount of data and feedback you can get from a BAS system is just so much higher. The velocity of data you can get, the accuracy you can get in your control, there's just really no reason outside of very few specialty use cases for you to be putting pneumatics in new buildings. So fast forward many decades, and central processing units, also known as CPUs, became cheap enough to put into controllers. Now, at first, these CPUs, they existed with some simple programs that were predefined. These were known as application-specific controls. You could change the program, but typically you needed to use some dip switches or jumpers to select kind of what program was running, because these were predefined in memory. There was really no way to change them. They were burnt into the memory. Now we move forward a little bit more, and we have some configuration software now. Now we still had application-specific controls. We were limited to them, but we could choose from a couple applications using software, so we didn't have to necessarily do it for hardware. And at this point, things became rapidly evolving, and we moved into this concept of free programmable controls, or FPCs. These were the big daddies of controls. This is really what took controls to the next level. And see, this type of controller, it allowed us to process a signal and drive an output just like application-specific controllers did. The only difference is that we could use custom code that was actually programmed by a field programmer to implement sequences that maybe weren't exactly executable through application-specific control logic. Now, both of these new controllers, ASCs and FPCs, so application-specific controllers and field programmable controllers, relied on a concept called DDC, which stands for Direct Digital Controls. These new controllers, they had set input types, and they later evolved to have variable input and output types, which were usually jumper selected. Now, before I go into these new controls and all about them, I just want to spend a second to talk about DDC, because I find that you tell folks direct digital control, and then they're like, what does that mean? Well, in the past, you actually would process an analog input, but now what happens is actually analog inputs, resistive inputs, they all come into a controller and they get converted to a digital signal. Now, this is really important because when they're converted to a digital signal, which is ones and zeros, the CPU within the controller can actually process these digital signals now. So because we're able to process these digital signals, we're able to be using programming. And we'll talk about programming, we'll talk about firmware in just a second. And also, eventually, these new DDC controllers, they needed to be able to communicate with the end user. I mean, it's all well and good to have this data inside your controllers, but if no one can visualize it, I mean, you hear that term all the time, right? We need to visualize our data. Well, if no one can visualize this data, then it's of no good. So then you have supervisory devices that come out. Now, we'll talk more about this in next week's episode, but suffice to say, supervisory devices use trunks, and trunks allow controllers to be interconnected. So controllers, as I mentioned, consist of an embedded processor and memory and several interfaces. These interfaces can both be inputs and outputs. They can also be RJ45, so Ethernet. They can be RS485, so MSTP. They can be wireless. They can be Bluetooth in some instances. So you have a variety of kind of interfaces that can be utilized by controllers. Now, within these controllers, there is memory, as I mentioned. And within this memory, you have both, what's the word I'm looking for here? You have erasable and non-erasable memory, basically. Slipped my mind, and I'm not going to actually Google it. I think EEPROM is what I'm thinking of. But anyways, in the non-erasable memory, you can have hard functions coded in. But for the most part, in the actual programmable memory, you have what is called firmware and active code. So if you've ever logged into a building automation device and you've used a manufacturer tool set to write code using graphical logic and even using line code logic, the functions of which you're calling, the AND gate, the OR gate, the flip-flop, the PID, those are all functions that exist in the firmware of the controller. So the firmware of the controller knows how to process this logic. So these logic blocks actually represent code. So They represent line code on the backside. You just can't see it in most graphical programming. It's called abstraction. It's where you separate the user from seeing that level of depth by putting a layer on top of it. So we mask the line code by using graphical icons like and blocks or blocks. So that way you don't actually have to write line code to achieve that. Well, firmware within the controller actually carries all those functions, as well as carries functions of interfacing and things like that. So you have firmware and you have active code. Active code is actually the code that is developed by the programmer and then typically downloaded via a programming tool into the controller. Some companies will call it downloading, other companies will call it uploading. I wish we as an industry would standardize on the name because that can be confusing as all get out. To me, downloading controllers is when you're sending the application to them, and to me, uploading controllers is when you're uploading information from them. I mean, that's what I define it as. Some folks will argue it's the reverse. Just be clear when you're communicating with people. Now, also on controllers, we tend to find that we have jumpers and we have ports, as I mentioned. Jumpers exist for a couple reasons, right? So typically our jumpers are there to go and set our input and output types. That's the most common type of jumpers. Now we also have dip switches, which are kind of like jumpers, but not really. Where jumpers, you typically will use your pliers or your hand and you'll pull them out and you'll put them over some pins. And those jumpers will pick between a DC input, amperage input, a resistive input. And then dip switches are typically for end of line, which we'll talk about in trunks, and MAC addresses, which we'll also talk about in trunks. So we have to realize that our controllers have network interfaces, and our network interfaces, they have addresses, and those addresses are physical addresses. Just like you have physical address for your house or physical address for your network interface card on your computer, you also have physical addresses for your controllers. Most often, these are MAC addresses, but sometimes they are also actual software addresses inside your controller, especially with newer IP controls where you have an IP address. So speaking of networking and speaking of communication, we have trunks. So trunks, also known as buses, are a way for controllers to communicate to one another as well as to communicate to supervisory devices. Now, the purpose of trunks is simply that you can put a trunk and you can connect it to a supervisory device and then run it typically in a daisy chain. That's the most common way that we do most of our wiring per the RS-485 standard, which is where MSTP, Modbus RTU, both of those utilize RS-485. I know Modbus RTU also utilizes RS-232, but for what we're focused on in this episode, we're focused on 485, and we're going to be focused on IP. So trunks, as I mentioned, they typically will daisy chain from one device to another, and across these devices, you will have a positive wire and a negative wire. And you sometimes will have a common to act as a true zero. And what will happen is that you will get digital signals that will be sent across the wire in series. Now, I'm not going to get into token slave passing. I'm not going to talk about MSTP in great detail. It's something we've covered in previous podcast episodes, and we also cover in our protocols course in really great detail. But just suffice to say that communication trunks exist to process data from the controller and from the supervisory device. So what happens now is we have these series or serial protocols, typically BACnet MSTP and LAN FT10. And these protocols, they communicate at a decent pace. Some of the older protocols communicated fairly slowly, but the newer ones communicate at a decent speed. So you'll often hear, hey, you need to do IP controls because of the speed of controls. It's not necessarily that the speed is so much faster. I mean, it is faster, don't get me wrong. The real benefit of IP is how the actual signaling takes place. So being able to signal, especially when you're utilizing a star pattern, which is basically an end-to-end run, the ability to have full bandwidth focused on a single controller versus shared bandwidth, as we see in serial protocols, is definitely a big benefit. Now, typically on these serial protocols, we rate their speed in baud rate, which is essentially a measurement of the change of state of the electrical signal. Now, it's really important that we understand when we're talking about trunks, three different things. One is polarity. So polarity is making sure that when we think about poles, right, we have a positive pole and a negative pole when it comes to voltage. So we want to make sure that our polarity is correct. We don't want to have our positive wires switching to negative. So we have it coming out the positive port on one controller and going to negative on the other controller. That will cause major collision issues and it'll just shut down your entire trunk. You see how these trunks are meant to work, and one of their greatest weaknesses are they're a daisy chain. So if something breaks in the line, it tends to take down everything else downstream from the controller. So that is why folks are moving. One of the big reasons why folks are moving to the star pattern, although the star pattern is much more expensive, it is easier to troubleshoot, it's faster because it's IP, and it is avoiding that dependency on the daisy chain. Now, we also see with IP controls that we are using things like ring patterns, which have the benefits of the star pattern, but they also have the benefits of the ring pattern. That's about as deep as I'm going to go into design patterns for IP controls. Once again, if that's something you're really interested in, that is something we discuss in our information technology course, where we go through IP controls. So we've got speed covered. We've got our serial protocols. We understand what they are. Now we have to talk about addressing. We need to make sure that we have a specific hardware address for each interface that is connected to our network. So if you were to visualize this, right? If you visualized a long line and then you visualized these devices, like think about a vine, right? A vine of tomatoes. It could be a long vine with multiple tomatoes or multiple strawberries coming off of it, right? Well, that's kind of what trunks are like. They're these long lines with controllers hanging off of them. And as we tap into this network bus, we have to have our addressing and our speed correct, and we need to be properly terminated so that we can continue to communicate upstream and downstream from our controller. Now, when it comes to controls and when it comes to trunks, there's much more to know. I'm giving you all about the 30,000 foot view. But if you remember that controllers are devices that are either application-specific control or free programmable, and they allow you to process signals and drive outputs. Then we utilize trunks to take the data that exists within those controllers, those physical and logical points, and we take the data that exists, and we take that data via the trunk to the supervisory device, which then consumes the data and puts it in a platform so that it can be visualized by the end user. So that's the traditional controls, but now let's take a look at some things that are changing. For one of the big things that is changing right now is due to the increase of CPU capabilities and being able to get a lot of horsepower out of a CPU at a cost that isn't prohibitive, we are now starting to see controls that actually have full-blown supervisory capabilities, meaning that they can run trunks, meaning that they can actually have user interfaces and point extensions and all sorts of capabilities that were normally limited to supervisory devices. So we're seeing this. Now, at this point, the cost point for these controls is still a premium. Anyone who tells you otherwise is full of crap. But the reality is that that premium can, in certain instances, actually be worth paying the premium. The thing is, if you think about being able to, especially in critical environments, have a user interface, have all of that supervisory capability closer to the edge, then you're able to actually process and control systems closer to the system. When you're talking about a air handling unit or a central utility plant that is determining whether a data center or a operating room stays functional, the extra couple $100 to invest in a more advanced controller is a very minimal cost compared to going and relying on a centralized supervisory device, which could potentially not be able to communicate with that field controller because of communication trunk issues. So you've always got to weigh the total cost, not just first cost. In addition to this, we're also seeing that these newer controllers are able to have analytics engines built into them. Now, let's talk about what an analytics engine is. That's just a fancy way of saying service. So if we think about our computer right now, if you're in front of your computer and you go to computer, as long as you're doing Windows, I don't know what to tell you with Apple, but with Windows, and you type in SER and services should pop up. And if you open services, like I'm opening it right now on my computer as I talk to you, you will see a bunch of services. Some are disabled, some are automatic, some are manual, some are running. These are all applications that are running on your computer. So when you think about your building automation system and it's sitting on a server, it's actually running typically a database interface service, typically a user visualization service, it's typically running a web server service. It's running a variety of services that you then are able to access through applications. Well, an analytics service is nothing more than that. It is a set of code that allows your controller to have analytics functionality. Now, some controllers have greater analytics functionality at the edge than others, but this is an area that I believe is going to be very important for the technician. Rather than having to diagnose things at the supervisory device, having analytics built into these edge controllers is going to provide the capability for technicians and companies that are forward thinking that train their technicians to really troubleshoot utilizing pattern recognition, fault detection, etc. So all of this is being built in to these controllers. The next thing I want to talk about these new controllers is wireless. You know, there's a lot of folks who get all up in arms in wireless, especially a lot of customers. They inherently view wireless as being more vulnerable because you can discover a wireless SSID. Even if you hide an SSID, which an SSID is simply the address or name of your access point network that you're connecting to. So even if you hide an SSID, you can still find it with scanner tools. But the thing is that wireless is using similar encryption level to physical networking. I would argue that in a lot of cases, actually physical networks like Ethernet are less secure than wireless because they aren't often properly secured for port security, making sure that you don't take multiple MAC addresses, making sure MAC address spoofing is handled properly. So wireless actually serves a pretty good purpose. I think it's gotten a bad rap because initially you have to realize how all this stuff is rolled out. I was with manufacturers, so I got to see how this kind of all happened. You know, product development comes up with a product, and usually how these products are developed is that one or two really big customers will be saying, hey, we need this product. Or you'll see a regional market area where you're losing business. You'd like to think that things are very strategic in product development, but quite often it is a reaction to the loudest noise. So these products come about, and then what happens is often there is a disconnect between product development and learning and development. And because of that disconnect, the field organizations that need to understand how to utilize this technology, and I'm going to let you guys in on a secret. I mean, this is what I do as a business owner. I watch what technology is coming out, and I'm betting on manufacturers to not properly train folks. So that way we create training that trains it. And I don't mean that as a dig to manufacturers. Just the reality is manufacturers are geared towards creating training for their products. Yes. But when it comes to training to these more technical things like wireless networks and IP controls, there's a couple folks out there that are doing it really well. You notice I'm not naming any names here because I'm not going to do that. There's some companies that do really good job of training their organizations and educating their systems integrators around these new technologies. There's some that don't. And wireless is one that when it originally came out several years ago, it was really poorly communicated to field organizations. You see, with wireless, you have to be able to design networks. You have to understand hotspots. You have to understand where dead zones are and cell handoff and things like that. And you also have to realize that traditional wireless design thought processes are different because our device locations are static. Our devices don't move around. So we can't go and count that, oh yeah, that's the dead spot, but it's only going to be a percentage of the time is that spot dead. Well, if your controller just happens to sit there and never moves, you're going to get poor reception forever. And this is something that a lot of folks didn't consider. And because of this, wireless installations failed and they weren't really reliable and they got kind of a bad name. I will tell you though that wireless is a great technology when properly utilized. So be aware that there's a lot of products coming out now with 802.11 wireless, which is really nice to see that folks are adopting the Wi-Fi standard because there's already existing access points in most buildings, and we should utilize those. All right, folks. So there you have it. That is building automation controllers and field trunks. I really hope that this is kind of helped to educate you around controls, help you understand controllers, helped you understand trunks, and given you a different perspective on how all these pieces of technology come together. I appreciate you taking the time to listen to this. Like always, everything I mentioned will be at buildingautomationmonthly.com/157. Once again, that is buildingautomationmonthly.com/157. Thanks so much for being here. I hope you all have a great week, and I can't wait to talk to you in next week's episode where we will be discussing supervisory devices. Thanks a ton. Take care.